Good afternoon, I'm Liang from Nanjing University. Very glad to be here to share our work region-based content enhancement for efficient video analytics at the edge. This work is jointly started by Nanjing University, Tsinghua University, and the University of Göttingen. Okay, let's start the presentation. So video analytics has been widely used in our daily life, like wildlife camera, like traffic camera, like drone cameras. Video analytics system architecture is shown in the figure. Camera first capture video frames and transmit them to the edge server for complex DNA inference to achieve a high accuracy, low latency, high throughput, and low resource overhead. However, video analytics is network resource intensive. Higher video quality improves accuracy, but also increases bandwidth. For example, high resolution like 1080p can achieve 99% accuracy, but cost about 11 Mbps. As a contrast, low resolution like 360p only cost about 1 Mbps, but achieve 81% accuracy. Therefore, existing work has introduced the super resolution techniques by employing DNN-based upsampling to address this challenge. And after SR, the system achieves about 94% accuracy, while only transmitting 1 Mbps data of 360p video. However, SR introduced additional computing cost. SR is 7 times flops and 4 times time cost than the analytical DNN, for example, like YOLO. So a more optimal solution leverages temporal redundancy in video streams by selectively applying SR only to the keyframe. Okay, selective SR selects a few frames as keyframes and perform SR on them and reuse them on continuous ones with some erosion. Okay, selective SR saves lots of computing resources while meet human vision app needs, like some video streaming. However, analytical tasks are more sensitive on image erosion. For example, the object detection task requires SR more frames to meet the setting accuracy. Okay, but we found that video streams have significant spatial redundancy where only specific localized region require high resolution analysis. And these regions are termed E-regions, which are enhancement-worthy regions. This region typically under 25% of the frame content shown in the figure, and this region represents visually ambiguous elements that low-resolution detections fails to recognize, shown in the left figure blue box. And so we can only enhance a small portion of content in each frame. But to achieve this, we need to solve one question: how to execute region-based SR efficiently at the edge. So we present RegenHance, a novel edge video analytics system that achieves a high throughput processing through region-based content enhancement. Our solution addresses 3 challenges. The first challenge is how to identify the region, and then enhance them and allocate resources among components to get a higher throughput. Okay, the first challenge is how to efficiently identify regions. We can see that if we only enhance in a region, yes, substantial system gains contributes about 2.4 times time saving. However, the region identification is a chicken-egg problem because reliable detection of regions itself requires high resolution analysis based on SR frame. Okay, we can use a simple idea. We can use IOI detection to identify the regions, but it is too costly. So our first technical is MB-based region importance prediction. We found that previous ROI method are costly as is pixel grain detection. And macroblock-based from video codec, we can be about 200 times lighter than the ROI detection, because macroblock is a 16 multiply 16 pixel block. So our first design is setting macroblock as the basic unit. It's both efficient and accurate. And our second observation is that identifying a region is a semantic segmentation problem. We can use the importance score to represent the impact of enhancing a macroblock on accuracy. And then we discretize the importance scores into quantized labels assigned per macroblock, enabling efficient region importance prediction, as shown in the figure. Therefore, we leverage ultra-light semantic segmentation models to predict region importance on MB level. And our light predictor can achieve 30 FPS per CPU thread and is 60 times than LI detection. Okay, the second challenge is how to enhance regions in high throughput. Regions are irregular and sparsely distributed in each frames. But efficient batching enhancement needs the same shape and enough size. And another question is that we need to enhance multi-stream concurrently. So regions to be enhanced must be considered holistic across streams. And otherwise, the potential benefits of region-based enhancement would be degraded. For example, there are two streams which have different potential gain. And we use a case study to show this. We firstly use round-robin method to select regions across streams and allocate the same size of regions to each stream. We can find that round-robin can only achieve 60.2% and 13.2% and 6.7% gain at stream 1 and stream 2. Leads to about 20% overall accuracy gain. However, if we can design a holistic region allocation, such as allocate more region to the stream 1, we can see that holistic region enhancement across streams can achieve a higher overall accuracy gain, about 23%. To solve this challenge, we need to select and enhance most beneficial regions. And our first design is that aggregates and sorts MBs across all video streams in order of importance, and keeps these MBs in a global MB queue, and choose the top end to generate the region. After we select the most beneficial regions, we need to perform SR on these regions. We observe that the latency of SR model is pixel value agnostic but shape aware. To minimize computational overhead, the input shape to the model should be kept as small as possible. Therefore, before enhancement, we stitch the regions into a smaller shape. We can formulate this problem as a bin packing problem and adopt two strawman method to solve it. And the strawman method detail can be found in the paper, and we only show the detail. This method either have a low occupy ratio or are too time-consuming. So to address this, we propose Tetris bin packing, a method that packs regions into a batch size and H multiply W bins according to their importance density. We use a case to show the benefits of our algorithm. For 3 irregular regions, our method first converts them into regular rectangles, and for the oversized region, like region 1, and we partition it into sub-region 1 star and 1 double star. And these regions are then sorted by the importance density and packed into the available area of the H multiply W bin through rotation, ordered from the highest importance density to the lowest importance density priority. For example, we first pick the region 2 and 3, and then we try to pick the region 1 star by the rotation, and drop the region 1 double star by rotation, and drop the region 1 star. Compared to the strawman approach that pack by maximum area, which include unimportant MBs, our method can achieve a 13% accuracy improvement. We also achieve a better occupy ratio with a low time cost. Next challenge is how to allocate resources among components. And our system has lots of hyperparameters like H and W and batch size. And these hyperparameters affect the efficiency of end-to-end performance and need to be ratio configured based on the hardware. Computing resources must be carefully allocated among the runtime components. The system workflow can be represented by the data flow graph shown in the figure. The pipeline consists of 4 stages. The first stage is decoding and identification and enhancement and the final analysis. We can employ a region-agnostic scheduler that executes all components sequentially. The system exhibits significant resource underutilization. Okay, so to maximize the utilization, we draw up the execution plan offline with the profile-based method. And our method first, we fix the DFG and the profile throughput of each component on the given edge with represent value. And then we generate the plan based on the max throughput batch size of different models. And finally, we load each component into the corresponding hardware. Okay, this figure shows that our execution plan achieves an efficient GPU-CPU cooperation. And finally, we put everything together and get RegenHance architecture. Okay. We conduct a comprehensive evaluation across diverse hardware platforms, including cloud servers, edge servers, and consumer-grade GPUs. And the experiments include 2 downstream tasks, object detection and semantic segmentation. And our approach was benchmarked against 3 baselines, the infer-only baseline and 2 selective SR baseline, NeuralScaler and NeMo. And we evaluate the performance of RegenHance on heterogeneous devices. We can see that RegenHance achieves about 12 times of NeuralScaler throughput and 2 times of NeMo throughut in A100. Okay, more detail can be found in our paper, like the contribution by individual components, like the system's scalability, like the visualization of our region-based content enhancement. Okay, let's do a conclusion. Content enhancement brings great benefits to video analytics, but perform enhancement or temporal selective enhancement fall short. Spatial region enhancement is spot on. So our contribution is design the RegenHance, region-based content enhancement video analytics at the heterogeneous edges. And RegenHance can achieve better accuracy and throughput trade-off and lower end-to-end delay. We have released our code in this link. Okay, that's all. Thank you.